Good morning to all of you. I am K. Palnivel, SNS College of Engineering, Mathematics. Today going to the subject name is Transforms and Partial Differential Equations for all second year branches in engineering. Today going to the case studies topic is a case study on retrofitting heat exchangers in industry. Introduction. We are going to introduction. Crude redefinitory preheat trains PHD. Preheat trains PHD are networks of heat exchangers that transfer heat from process streams to the crude in order to raise its temperature before it enters an atmospheric distillation column for fractional separation. Up to 70% of the heat required is provided by the PHD preheat trains. The remaining heat is provided via fired heater. Fouling in PHDs is a major economic and environmental problem as it reduces thermal efficiency and throughput capacity of the system. Identifying effective methodologies to manage PHD fouling remains a key research area. A typical PHD include such as desalter and free flows tower, which are required to operate within a constrained set of operating parameters. The PHD is followed by a fired heater, which itself has a maximum furnace duty limit. Crude oil fouling is a complex phenomenon. Fouling is caused by different mechanisms at different locations on the PHD. As a consequence of different chemical and physical mechanisms, chemical reaction fouling is known to be the dominant mechanism downstream of the desalter. Chemical reaction fouling is the formation of deposits on heat transfer surface where the fouling precursors are generated by chemical reaction. Two types of reactions are common. First one is formation of gums. That is when the sulfur content of the crude is high, the decomposition of maltines to produce insoluble aspaltanes are complex polynuclear aromatic compounds and often the case for chemical reaction fouling in this part of the preheat train. Other reactions, such as those catalyzed by FeS ferrous sulfate and other corrosion products, could also be present. Water carry over from the desalter can result in rapid fouling of exchangers operating at the temperature at which the water evaporates. These exchangers are easily identified. These exchangers are easily identified. Careful analysis of monitoring data provides useful diagnostics. Several quantitative models for calculating or estimating crude oil fouling rates have appeared. Following the introduction of the fouling threshold concept by this one, the semi-empirical approach originally introduced to evaluate the rate of crude oil tube side fouling at a local point condition describes the fouling rate as the combination of deposition term and a fouling suppression term. The rate exhibits two primary dependencies. First one is increase. First one is the increase with increasing surface. Second one is decrease with increasing flow velocity. increase flow velocity. The concept has become an accepted basis for the development of many heat exchangers design and control strategies as reviewed. Complete mitigation of the fouling in refinery PhDs is rarely achieved, and periodic cleaning of fouled exchangers and the scheduling problem of when and which units to clean have been widely researched within the numerical optimization community. In this manuscript, the hydraulic aspect of the crude oil fouling is revisited. The crude is pumped via centrifugal pumps. These pumps are usually operated under constant rotational speed and are designed to maintain a target throughput even as the network pressure drop increased with fouling. Control of the throughput is achieved through partial opening and closing of the control valves and bypass streams. PhDs can expertise hydraulic limitations in two ways. Fouling cases an increase in resistance to flow if the flow resistance increases to the extent that the centrifugal pump is unable to deliver the required throughout reduction in throughput will occur with the buildup of foulant. Falling reduces the thermal efficiency of preheat train. This results in the reduction in the coil inlet temperature and increase in the required furnace duty. Once the furnace is unable to deliver the required heat duty, a reduction in throughput will occur to deliver the crude at its target column inlet temperature. This methodology discussed to mm, this methodology discussed too. The formulation was based on non-convex mixed integer nonlinear programming methodology. The dynamic falling models nor a rigorous furnace model. The aim of this paper is the case study is to model dynamic falling behavior in the operating PhD and to evaluate which would result is in a greater benefit through retrofit actions and also to explore possible changes in the network structure. Commercial computer programs from IHS, Smart PM and Express Plus were used for this case study. The Smart PM software is built upon the combination of advanced heat exchanger network simulation and cleaning, scheduling methodology, and industrially accepted shell and tube heat exchanger design and rating technology. The network simulation code was developed at the University of Cambridge as part of the EPSRC funded crude oil fouling research program. The heat exchanger design technology was developed for the computer program Express Plus and re-implemented in Smart PM. The techniques described in this manuscript are incorporated into Smart PM. Smart PM will hereafter the referred as the simulators. Next one, model description. The thermal performance, the individual, first one is the overall heat transfer coefficient, second one is fouling rate, third one is scheduling. We are going to the first one, overall heat transfer coefficient. The thermal performance of individual heat exchangers is modeled using the over heat transfer coefficient U as the sum of thermal resistance in series. Here 1 by U A naught equal to 1 by H naught A naught, H1 HI A 1 plus 1 by HI A plus RF divided by A, etc., etc. Here A0 is external heat transfer area, A is the internal heat transfer area, RW is the wall resistance, HI is the internal film transfer coefficient also. The fouling rate. The chemical reaction fouling model for tube or shell side deposition presented presented the place was used the quantify the rate of fouling in this study. The falling resistance is given the above. The variation of the hot stream flow rate is assumed to be proportional to the variation in the crude stream flow rate. Fouling with the fired heater was not considered in this work. Scheduling. The cleaning scheduling formulation is based on the heuristic algorithm formulated by some authors. The objective function is to minimize the total economic impact during the operating period. Total economic cost equal to cost of energy plus cost of lost. This is this one is the total economic cost. Total economic cost equal to cost of energy, cost of lost. Throughput margin plus cost of lost throughput margin plus cost of cleaning is the total economics cost. Next, we going to PhD network. The medium and hot sections of the PhD are presented in the following figure. See this, the diagram. The PhD studied is the part of the Petronas refinery at Gromouth, UK. Gromouth of the refinery relatively old as the construction dates. The medium and hot the sections is given. The crude enters desalter around 110 degree and its temperature is raised to 150 degrees Celsius via exchangers E1 to E2. The crude passes through the flash tower and is then heated to 205 degrees Celsius before entering the furnace. The current capacity of the PhD is 52,000 bpl day inverse per day. The coil inlet temperature over 10-month period is reported. During this period, a turnaround took place after 7 months, where all the units in figure this clean the diagram is cleaned before this coil inlet temperature. The case study of this the network is the going on. The cleaned design conditions of the exchangers are also given. Design condition exchanger labeled E in summarized the tables. The exchanger ELAB, ELCD, E2 ABCD consist 2 to 3 and 2 shells in series respectively. If these units are to be isolated during a cleaning action, all cells in series have to be isolated due to the location of the isolation valves, the locations where the temperatures, flows and pressure are mentioned, monitored, or marked in the PhD diagrams. Not all stream temperatures and flows are monitored, hence, it is necessary to generate the missing information before evaluating the fouling behavior of each cell, the data recognition methodology. The simulator was employed to generate automatically the missing the streams. The exchanger also is given. The fouling resistance profiles for cells E1 ADC, the focus the disturbance of volumetric flow, the cold stream, ELAD evident. The thermal resistance profiles for each cells are different with higher thermal resistance in the hotter unit. The following cleaning event, the exchangers exhibit a minimum resistance. The falling profiles quasi-linear. When the desalter inlet temperature is not controlled, the units the downstream can be subject to inorganic salt crystallization falling. And also, the desalter temperature here was controlled and around 110 degrees Celsius. The slopes of falling resistance. The slopes of falling resistance profile, the falling rates were found to be a strong function of operating temperature and flow rate. Regions of table operations were identified for each exchanger within the simulator, generating a matrix of operating periods. The corresponding falling rates and operating data are used to evaluate parameters for falling models such as above equations. This allows the modeling for falling performance in periods where particular crude blends are processed, hence allowing a database of crude isolates the specific falling model parameters to be constructed for use in simulation and cleaning calculations. Cleaning the calculation, the falling parameter in equations evaluated the regression analysis fitting the value to minimize the sum of differences between the observed and predicted falling rates using this one. For each heat exchanger, the reliability of the fitted falling model parameter was tested through simulating the historical performance using the observed inlet conditions and the initial falling resistance as inputs for the network. The simulation results are plotted as dashed lines using these equations. With the exceptions, the simulated falling profiles matches the reconciled data well. A possible reason for the discrepancy out of the under the predicted the equations is the process stream the falling occurring systems. The process stream falling is occurring which could be accounted for separately. Next one is the falling rate on the process side. The vacuum residue stream is known as the redefinery of case the falling of the exchanger by the stream has not been visually confirmed, but we have to acknowledge this possibility based on experience. Past refinery experience also. Next one, during the data reconciliation period, the PhD was operated to achieve a target throughput due to the furnace reaching its maximum capacity. The gradual reduction in throughput has occurred. The operating condition of the furnace is summarized. Taking the PhD operating parameters at the beginning of the data reconciliation period as the starting point, the CIT and throughput profiles were simulated. The targets was assumed which would decrease in the if the furnace is usable unable to provide the required duty throughput was obtained. The section AB is region of constant throughput where the furnace is able to accommodate the reduction in CIT at the target throughput as the furnace has not reached its duty limit. Section BC presents a region where there has been reduction in throughput as consequence of the furnace reaching its maximum duty with falling. Therefore, that the falling model together with the crude thermodynamic data, network simulation model and furnace model was able to predict the historical plant behavior. Simulation studies of the future performance are now executed to evaluate the best methodology to manage falling the PhD. In the case studies, the objective of the PhD is to operate at maximum throughput in contrast to a target throughput. Hence, only equations the used to evaluate the throughput equation rather than the equation. Next, the result of heat pump integration. Uh, First, we get to the simulation scheduling. The study evaluated the scenario where PhD is operated without any cleaning modifications. Modifications. Also, the study networks, slopes of the falling resistance, result of the heat pump integration, and the simulation and scheduling. Also, the results of heat pump, the heat put of the pump increase with the increase in cooling the edges. There is a steep increase when the saturation temperature is reached outlet energy. The output reaching the heat output of the heat pump is compared to the Total thermal energy that is the needed that this production depending on the initial exhaust gas temperature up to 10 to 55% of thermal energy can be provided by the heat pump. Simulation and scheduling. The simulation and scheduling of the original network with a specified maximum furnace heat duty. This study evaluated the scenario where the PHT is operated without any cleaning or modifications to the network. This was done by taking the reconciled data set 1 month after the turnaround obtained from reconciled results, the starting point. During this period, the crude processed had an average the crude process had an average API gravity of around 33 APA. The thermophysical properties of the stream are detailed below table. Operation was predicted for the period 31 months. At the start, the furnace is operating under its maximum duty. Hence, with the decrease in PhD thermal efficiency, solid line in the following energy. Next one. Going to the furnace performance. The parameter and the values are given. The parameter is maximum capacity 50 MWs. The furnace outlet temperature is 360 degrees Celsius. Furnace inlet pressure 9 para. Furnace outlet pressure is 2 para. The following diagram is turn around simulation data reconciliation. First one is coil inlet temperature. First one diagram A is coil inlet temperature. The starting degree is 122, ending degree 220, 120, 140, 160, 180, 200 and up to 220. They reached the 200. This is the diagram, the graph. Second one diagram is throughput. Simulation data reconciliation is starting is 65, ending is 95. The reached the diagram, the chart is 85. 65, 70, 75, 80. 85 is the reached the diagram. Variation in coil inlet temperature and throughput with time. Symbols present a reconciled data. Solid line shows simulation trend. Also given. The reduction throughput to below the 60 kilograms during the 30-hour simulation period represents significant loss in margin. Now consider the cleaning as a mitigation strategy. Use the tube inserts of E3AB. E3AB is a major component that divert all crude flow rates also. Next on installation of the tube. The tube inserts were identified the subjects ever falling. Tube inserts were identified as an option to increase the tube side wall shear stress, which would reduce the rate of falling. Twisted tapes were selected on the basis of the allowable pressure drop and the ease of installation. Furthermore, twisted tapes could be fabricated on site. Divert all crude flow rates to E3AB after the free flush. The exchanger E4 has the smallest duty in the network. If there is sufficient cooling water duty available to cool stream 4, the diversion of crude to E3AB will further increase the wall shear stress to reduce the falling in the long term and the pre-desalters. Pre-desalters also. And ideally, preparatory options minimize the disruption planned operations. Changes include a different bundle geometry or use of the tube inserts which can be done offsets. Here we consider the use of tube insert E3AB. Twisted tapes are in common use due to their easy fabrications. An insert with 360-degree twist over a 100 mm length is considered here. Helical coil wire is also considered in parallel to the twisted tapes. Hydron is another common tube insert which is able to maintain particulates in suspensions. It is commonly employed in non-fouling situations to improve heat transfer. Use of tube inserts increase the tube side pressure drop. heat duty network. The following chart is the heat duty networks is given. The benefit of case studies to immediately evident through the initial increase CAT subsequent reduced the rate of decrease in both CAT. The throughput case study provides the superior over longer operating period. The variation of exchanger heat duty is the time is given the following chart. The economic benefits of case studies are compared or month period. The finance operating its maximum duty. Any difference in the economic performance. Finally, we go into the conclusion. Finally, we are going to the conclusion. Plant monitoring data were reconciled to generate falling resistance profiles for each cell. A dynamic falling a dynamic falling rate model with parameter A equal to 450 per hour was identified and give reliable simulation of PhD performance. And the crude refinery preheat trains are major part of the refining process as these units reduce the amount of the thermal energy required to the heat the crude oil to its the distillation temperature. Falling is the long-standing problem in the operation PhDs. The ability to refinery to process the different crude blends or to increase its production capacity depends on the thermal and hydraulic performance of the PhD under falling conditions. Okay, uh, which enable falling behavior to be identified based on operating flows and temperatures, techno-economic analysis for heat recovery and falling mitigation, including retrofit of heat exchangers. Use of its tube inserts the network revamp were conducted. The commercial software tool Smart PM was successfully utilized to study heat recovery paths, cleaning schedules, the furnace firing capacity on this case study. The furnace model was implemented, which enabled the simulation of the reduction in throughput with the falling under operation of maximum furnace duty. Simple retrofit actions together with the optimized scheduling were successfully shown to significantly reduce losses due to falling. Optimized cleaning have a benefit in improvement at least 3 times larger than a benefits based on hardware modifications alone. These are the case studies is studied well in the case study on retrofitting heat exchangers and revamping preheat trains subject to the falling. Thank you. Thank you guys. Thank you.